So today the main topic will be catalysis, but first I want to go into a number of factors that can affect reaction rates. And we didn't really talk about that in a lot of detail, but it can be quite important under certain conditions. Okay, so let's start with that. So factors affecting reaction rates. And we're always going to talk about bimolecular reactions. So K2, that goes to some product P. Okay, so of course, a very important factor is the solvent. And you all know that probably from if you've done any lab work and chemical synthesis. But so we know from transition state theory, this is just a reminder that this second order rate constant is Boltzmann times temperature over the Planck constant, exponent minus delta G standard of the transition state over gas constant times temperature. Okay, so if we split delta G into 2, right, we get exponent delta S. I'm just splitting delta S in, or delta G in S and enthalpy. Okay, minus delta H. So the enthalpy of the transition state over RT. So this delta S is of course the standard entropy of activation. Delta H is the standard enthalpy of activation. And just for fun, let's take ln of both sides and divide by temperature. So we get kT over 2 is ln Boltzmann over H plus delta S standard of transition state R minus delta H of the transition state standard over RT. So now if we look at this equation, we can try to see what are constants. So Boltzmann is a constant, Planck is a constant, delta S doesn't have a dependence on temperature, the gas constant neither, delta H neither. So we basically have a lot of constants. So if we would plot ln of K2 over T versus 1 over the temperature, we would get a straight line with a slope that is minus delta H of activation over R. Okay, so let's look at an example. So let's say we have a reaction, we just call it reaction 1. And I'm going to color some of the groups. So we're going to take triethylamine plus ethyl iodide. Okay. And this is in an equilibrium with a transition state. Sorry, move this a bit. It's not going to fit. Okay, there we go. So we have ethylamine iodide, delta plus, delta minus. Here's the other ethyl group. Okay, so I'm drawing the transition state. Right, this is the transition state. And then we continue ethyl 4N plus I minus. Right, so you can see that the transition state, transition state is highly polarized. Okay, so now imagine if we put this reaction in a polar solvent, what will happen? The transition state is more solvated, right? So that means the solvent molecules are highly oriented around the transition state. And highly oriented solvent molecules is not very favorable, right? So the result is we have a loss of entropy. So delta S here is much smaller than 0. So that's an entropic effect. Also, if you look at delta H of the transition state, it is the enthalpy of the solvated transition state minus the enthalpy of the reactants solvated. Okay, so here, if we are in a polar solvent, this will be lower. So the result is that delta H of the transition state is smaller. So if we look, for example, for reaction 1, we have delta H of the transition state is 64 kilojoule per mole in N-hexane. It's 49.5 kilojoule per mole in bromobenzene. And it's 45.5 kilojoule per mole in nitrobenzene. So you see, we're increasing the polarity when we go down this row of solvents, and that results in a much lower activation enthalpy for this reaction. So this is, of course, all organic chemists know how to play with these conditions to optimize their rates and their yields. But it's good to understand how that works. Okay, maybe something less intuitive is pressure on the reaction. So this is hydrostatic pressure. Right. So of course, if you're in the gas phase, it makes sense that pressure makes a big influence, but also in the solution state, you can have effects. So how does that work? So we start again from this rate constant from transition state theory. Okay, exponent minus delta G transition state not over RT. And we'll just take the ln of that whole equation. So get kBt over Planck minus delta G over RT. Okay, and then you probably know that dg is v dp minus s dt, right? So the change in Gibbs free energy is volume times the change in pressure minus entropy times the change in temperature, right? This is in a closed system. And from this, you probably know that if we take the partial derivative of dg with pressure at constant temperature, this T here means constant temperature, this equals volume. Okay, so this is just from basic thermodynamics. So let's now differentiate this ln K2 equation, and we take the partial derivative with pressure. So we get d ln K2 dP at constant temperature. This will be d ln Kb T over Planck dP at constant temperature. This is actually, we'll see, whoops, we'll see later that this is 0. We'll just draw it out for now. D delta G not transition state over RT dP at constant temperature. Okay, so this term is 0. Okay, so what do we get? And we know, if you look here, that this derivative of G with pressure is volume, right? So we're going to stick that here. So we end up with the ln K2 over dP temperature is minus delta V over RT. So this thing is called the volume of activation. Okay, that's fine. Like, let's look what kind of impact that would have. So let's say we are performing a reaction at different pressures. Okay, I'll just put some numbers so you have some idea. 2, 4, 6, 8, 10. One. So this would be ln K2 over K2 naught. So that naught means without pressure. So this would be if you run the normal reaction just at atmospheric pressure. And this will give straight lines. And, well, okay, maybe I don't have to give all the examples. I'll put some more examples in the notes. But for example, for this reaction, so that's a hydrolysis. So the hydrolysis reaction, this, by the way, so 100,000 Pascal is 1 bar. So this is 100 bar, right? Your bike has like, the wheels in your bike have something like, 2-3 bars of pressure normally. So if you put some serious pressure on your reaction, and that can be done, for example, in a power reactor, you can easily reach 100 bar. Then you can really significantly accelerate your reaction. So that's a bit less straightforward, but again, used in organic chemistry a lot to accelerate reactions. Okay, let's look at another factor that can change your reaction rate, and that is the dielectric permittivity. Okay, so this holds when the reactants are ions. So we saw before this Coulomb force, right? Which is ZB times E. So this is just the charge on ion A. So E is the elementary charge, right? So Z is a number, -1, 1, 2, okay, divided by 4 times pi times E naught, epsilon naught times Kr times R squared. So epsilon naught is the vacuum permittivity. Kr is the relative permittivity, which has actually no units. And R squared is the distance between the ions. Okay, we already saw that in a previous class. So let's put some numbers on this. Okay, so if we have Kr and we say, okay, vacuum, methanol, water, chloroform, and for example, DMF, then, so by definition, the relative permittivity of vacuum is set to 1. And then methanol, it is 30, water 80, chloroform 4.8, and DMF 36. So you can see that there are really huge differences between these relative permittivities of different solvents. So if you have ionic species in your reaction, it's very important. So for example, if you look at LnK2 versus Kr minus 1, again, let's put some values here. Oops. Okay. And we have 0, 2, 4. Wow. Okay, up. So this is a reaction, bromophenol blue plus, it's basically a pH indicator. And then in different, I'll give you the reference. So it's Jax 1939, pretty old. Okay, so it's basically color change in this bromophenol blue indicator at different water methanol mixtures. So here, if you take 1 over this value, you have around 80. So this is pure water. Oops, pure water. And here, you're about 1-to-1 water methanol. Right, so you can see that there can be really drastic changes in the rate constant if you play with the dielectric permittivity of this charged, these are ions, right here, OH minus. Okay, so that's dielectric permittivity. Let's look at another factor, ionic strength. Okay, so you have to be, again, ionic reactants in a solvent of high dielectric permittivity, let's say water, then the rate constant will be proportional to the ionic strength. And so this is called the primary kinetic salt effect. Okay, and I'm not going to derive the whole thing. I'm just going to give you the result. So if we take log 10 of K2, it will be the log 10 of K2 naught. Again, this is the rate constant in absence. Oops. Effects, salt effects, plus some constant times ZA times ZB. So this is the sign of the charges, right? So this can be +1, +2, whatever, times the square root of I, 1 plus the square root of I, where I is the ionic strength. And that's in units of molar. Right, so practically speaking, you can just add a bucket load of sodium chloride to your water to change the ionic strength, which will change your reaction rate. And that can lead to increases or decreases in the reaction. So let's look at an example. Okay, so if I put 0, 0.05, 1, 0.15. So here I'm putting square root of I over 1 plus square root of I. And here I'm putting log 10 of K2 in per molar per second at K2. Okay, so for the first reaction, I want to show looks like this. So this would be iron 2 plus cobalt complex. Okay, so here we actually observe a decrease in the reaction rate, whereas for another reaction, I'll draw another axis here. Minus 0.8, this would be iodine plus S2O8. Right, so it depends. It's not universal that it will always accelerate or decelerate. It really depends on the reaction you're looking at. Okay, because here, let's look why that is. You know, here, of course, in the iron 2 plus reaction, you have a positive and a negative ion. Right, so they are actually attracted by Coulomb forces. And if I salt it out, right, I add a lot of salt, I'm screening those charges. So they are less attracted. Whereas in the iodine case, you know, they are both negatively charged. And so if I salt it out, I increase the ionic strength, actually, I increase the overall rate. Okay, so that's interesting to observe. Okay, let's move to another effect. That's the effect of isotopes. So there is something called a kinetic isotope effect, KIE. and it's the rate constant L over KH. So what does this L stand for? It stands for light atom and heavy atom. So for example, you could compare hydrogen to deuterium. So actually that is the biggest change you can get, right? When you go from hydrogen to deuterium, the mass of the atom increases 100%, which is a lot, right? But let's look at an example. So if I have this reaction, cyanide plus methyl bromide. Okay. Okay. So this is a SN2 reaction. And I'm going to copy this. Okay, and now I'm going to use some isotopes. Okay, so I'm going to just color this a bit differently. So this would be carbon 13 labeled, right? So you can just buy carbon 13 enriched reactants, right? And so normally, so as you know, carbon is normally 12, right? We don't write it because the most abundant isotope, you just you don't indicate it. But if we use carbon 13, we can actually have a difference in reactivity. So here, the kinetic isotope effect. So this would be L and this would be H, right? Would be KL over KH. This case is 1.082, plus or minus 0.008. So it's only a 8% change in the reaction rate, but it's noticeable, it's measurable, and actually it's used to elucidate reaction mechanisms, right? So make a little comment about that. So what are the observations? So usually you need greater energetic input to reach the transition state for the heavy atom, right? So it's useful to study reaction mechanisms. Why? Okay. Imagine this reaction of cyanide and methyl bromide would go through an SN1 reaction. So SN1 would mean first the leaving group, so bromine would go off, and then the cyanide would attach and you would get the product. So if you would do an SN1 reaction and the rate limiting step is the the leaving group going off, you wouldn't see any difference between KL and KH. But since here we're dealing with an SN2 mechanism, so there's a transition state where this cyanide is directly interacting with this carbon 13 labeled atom, you see an effect in the rate constant. So people use that. They think, okay, what do I think is the mechanism? Where can I put a carbon 13 or a deuterium to change the rate constants? I measure it under the same condition. If the rate constant is really different, then I can prove that that atom is really involved in the reaction mechanism. So we can split it into two effects. One is called the primary kinetic isotope effect. So that means the bond to or from the isotope labeled atom is broken or formed, right? And then you have the secondary kinetic isotope effect. That means no bond to the isotope labeled atom is broken or formed, right? So the secondary kinetic isotope effect is much smaller. But for example, so KIE secondary of hydrogen to deuterium, because there's such a big mass difference, can be up to 1.4. That means 40% change in the reaction rate, right? So the secondary effect for hydrogen to deuterium can be larger than the primary one for carbon, because carbon, you only, from carbon 12 to carbon 13, you only have a small change in mass, whereas from hydrogen to deuterium, you said the mass increases by 100%. Okay, so let's move to another important effect, and that is of electron transfer. Okay, let's say we have a reaction. Cerium 4 plus iron 2 plus gives cerium 3 plus iron 3 plus. So we didn't make or break any bonds. So if we will look in general in an ion in solution, it will have solvent molecules around that are interacting with this ion, like hydration. So these are solvent molecules. And the solvent molecules, of course, they move around, right? So the hydration shell, the solvation shell around this ion is continuously changing due to thermal fluctuations. Okay, so a very smart person came along. Oops, let me draw first the energy. So if you look at the Gibbs energy, G, right? If I have, oh, that was ugly. Okay, so here I have my reactants plus solvent. Then, of course, my lowest state I'm here, but there's always a bit of variation. So there's always a certain population along this curve, a bit left, a bit right, where the solvent shell is changing and therefore the reactivity is changing. So the same goes for the product. Product plus solvent. And so there's a theory, it's called the Marcus theory. So Nobel Prize 1982. Okay. Again, I'm not going to derive the whole Marcus theory. I'm just going to give you the results so you get an idea of what's important. So Kr, reaction rate, A times exponent minus lambda for RT 1 plus delta G naught over lambda squared. Okay, so this, let's look at the different terms. So this A is a factor that depends on the type of electron transfer. And this lambda is a solvent reorganization term. Okay, so why do we care? What does this mean? Let's look when we take ln of both sides. So we get ln r, ln a minus 1 over 4 lambda r t lambda plus delta g squared. Okay, let's plot this. So here, if I put log 10 of kr, ln kr, right? Units per second. And here I put minus delta G in kilojoule per mole. I put 0, 100, 200. What's strange about this? Okay, is that the rate is not monotonically increasing with a bigger delta G, right? You have a maximum. If you look at this term, you know, I have something minus another factor. So if delta G, sorry, not delta G naught is equal to this lambda, I'm at my maximum. So this kind of makes sense, right? So if you are in this regime, right, this is kind of common sense. So, but here you have a decreasing rate, and that is weird. Okay, I'll give you some examples if you want to look in more detail. But there's a nice Jack's paper, 1984. And so that is following the Marcus theory. And you have also examples, of course, that don't follow the Marcus theory. So Israel Journal of Chemistry, 1978. Okay, again, I don't want to go into all the details because it will take half an hour to explain. But so keep that in mind when you look at electron transfer reactions, that Marcus theory can actually help you to explain some counterintuitive effects like decreasing rate with bigger delta G. Okay, so let's move to a new topic, and that is catalysis. Okay, so the word catalysis or catalyst was introduced by Berzelius in 1835. And I'm just going to give you a slightly modified definition from the UPAC Gold Book. So a catalyst is a substance that increases the rate of a reaction without being used, nor changing the overall delta G standard. Right, and you've probably seen these kind of schematic drawings where I have Gibbs here, I have my reactants A plus B, I have my product P, and if I have the normal path, I have a certain activation energy, and if I have one with a catalyst, then this is much lower. Okay, so if we talk about catalysis, we can basically divide it in two main sections. The first one is heterogeneous catalysis. Catalysis. So if we look at how that's done, of course, heterogeneous catalysis in the industry is big business. So typically they use some sort of suspended catalyst on a solid support. So they have some kind of particle, okay, something like this, where this is solid. And it has pores, and those sizes can be quite different, can be millimeters to nanometers. For example, zeolites, etc. And typically you have some kind of metal particles that are on this catalyst. Okay, a lot of catalysts are metals. So in this industrial kind of catalyst, you have a large surface area. So also a lot of reactions, right? Then if we look how these things are studied, typically they are studied on as a model catalyst. So you would, for example, have a silicon wafer with a layer of silicon oxide, and then they would try to get the same type of metal nanoparticles. Doesn't have to be nano, can be millimeter, can be whatever size, on that support. So this would be a model catalyst. And if you go to academia, people even look at single crystal catalyst, right? So you would, for example, take a lattice. Okay, and study the catalysis there. So this would be single crystal. Right, so there's kind of different levels of zooming in. So here I zoom in, and here again I zoom in. Okay, so let's look at an energy diagram or Gibbs free energy diagram of such a catalytic system. Bigger. G, and here I put my reaction coordinate. So again, I start with my reactants. Then I have a state where I have absorption. I have my reaction, and then I have desorption. So let's look at those steps. So let's say here we have a molecule AA and BB. Okay. Then I have my catalyst surface, say a two-dimensional thing where AA and BB are absorbed. This would be adsorption and maybe dissociation. Here I form my products. So I have, let's say, 2 times AB on my catalyst surface. And here I would have AB 2 times in the gas phase, let's say. If we look for a gas phase catalyst, so here we are in the gas phase. So if we would look at the reaction without catalyst, we would have to do probably something like this, right? So we'd have a very large activation barrier, whereas here desorption is typically almost without barrier. Okay, I don't want to draw it that straight. Okay. Then we have here a typical activation, right? So here we have the EA with catalyst, and then we have desorption, which also has almost no barrier, but let's draw it like this. Okay, so those are the different steps that you would go through for a heterogeneous catalyst. You can't hear me? Sorry. Okay. It seems that most people are okay. Okay, I continue. Okay, so let's look closer at adsorption. Which is typically the first step when you do heterogeneous catalysis. And this we can divide into 2 effects. Oops, physisorption and chemisorption. Okay, so what are the differences? Some color here. Okay, differences. Physisorption is quite weak. Chemisorption is strong. Physisorption can be multi-layer, whereas chemisorption will be a monolayer maximum. As the word sounds, chemisorption, you have to do a chemical interaction reaction with the surface. So if you have a second layer, let's say you have a surface, and let's say this is gold, probably know that thiols can make a covalent bond with gold. So you could have like thiol gold interaction. That's chemisorption. But then maybe there's a second layer of this surfactant, which maybe attaches with these alkyl chains here, which would be physisorption, right? It's a reversible weak interaction versus a strong chemisorped interaction. Okay, so let's look at enthalpy. So delta H standard here would be -20 to -50 kilojoule per mole. And for chemisorption, this can be +30, that's weird, right? To -700 kilojoule per mole. Right, so you can have even a chem absorption can be endothermic instead of exothermic. But typically, in most reactions that we look at, it will be exothermic. And this is reversible. And this is mostly or often irreversible. Okay, so absorption can be modeled using various what's called isotherms. Okay, so the most famous isotherm would be the Langmuir isotherm. Oops. Okay, this can be derived in a lot of different ways, but I like this one. So imagine you have a surface and you have kind of absorption sites. We'll call it S. And I have some compound or molecule A, K adsorption, K desorption. And so here I would have A adsorbed. So this species I will call A ads. Okay, so let's look at the rates. So R adsorption would be K adsorption times the partial pressure of A times the number of sites S. Okay, so A is partial pressure and rate desorption would be Kd times the number of adsorbed A species. Okay, so we can now write the equilibrium constant, Ka will be K adds over Kd, which would be concentration of A adsorbed over Pa times S. Okay, and we can do conservation of mass. So we know that the initial number of sites, this holds at any time, right, is the number of free sites plus A adsorbed, right? So a site is either free or it's occupied by an absorbed species A. So from here, we can substitute that. Right, we write out S here, we fill it in this equation. So we would have A adsorbed over Pa times Ka plus A adsorbed is 1 plus Ka times Pa over Ka times Pa times A adsorbed. Okay, and now we're going to define theta, which is the coverage, the surface coverage. Surface coverage, which will be the number of adsorbed or occupied sites over the total number of sites. So that, if you look from here, right, just divide that by S0. Right. Ka times Pa. Okay, now I'm actually looking. Okay, I have to check something, but let's look at the result. So if I plot partial pressure versus surface coverage, 0, 0.5, 1, I would get something like, okay, just a second, something like this, right? So if I put a lot of pressure on the surface, I will start to saturate. The surface. So all the binding sites will be full. So there are basically two regimes. So there's the very low pressure or concentration if you're in solution. So Ka times Pa is much smaller than 1. So then the surface coverage is roughly Ka times Pa. Then there's the regime, very high pressure or strong absorption or high pressure. So that means Ka times Pa is much larger than 1. Then theta is about 1. That means there is a permanent monolayer of A on the catalyst surface. Okay. So Langmuir wasn't, of course, the only one that thought about this. So there are a lot of other isotherms, some more famous than others. So the SIPS isotherm is very similar. So it's Ka times Pa over 1 plus Ka times Pa. So this is basically Langmuir, but SIPS has just to the power alpha here. And so the nice thing about SIPS, so what you implicitly assume with the Langmuir isotherm is that let's say the binding energy of the site is the same for all sites. What you have in the SIPS isotherm is you say, okay, not all the binding sites are the same. They have some kind of distribution of energies. Maybe, if you stuff a particle really hard together, the microenvironments can be slightly different. And therefore, you can have a very broad distribution of different types of binding sites with different binding energies. And therefore, your absorption isotherm becomes this kind of, you get an additional factor in there. Okay, there's the Freundlich isotherm, which is alpha times Pa to the beta. These are mostly just derived. Langmuir, we just derived it, of course, but so these additional terms are just added because they did experiments and the Langmuir model didn't fit. So you have to add something to explain those things. So they usually are first derived from experiments and then later rationalized. Okay, so this is the Todt isotherm, which again, it looks very similar to Langmuir. So again, you raise the pressure to some power, you have some prefactor alpha. And this one is also very famous, is BET, which stands for Brunauer.
Sorry to interrupt you,
Yeah.
Professor, but you have invert the theta equation.
Yeah, I was thinking that multi-layers. All right, let me adsorption. Yeah, now when I was writing it, I was like, hey, if we divide here, then of course that cannot be right. I'm just trying to think, where did I go wrong? 1 second. Hey, Langmuir. See my derivation. Where is it? Yeah, okay. Of course, this should be inverted. Because I divide here, so this flips. Right. Okay, let's erase this. So this would be, sorry about that. This will be Ka times Pa over 1 plus Ka times Pa. Let me check. Yes. Should be good. Okay, yeah, sorry, I just messed that one up. So this is the correct one. Just did my division wrong. Okay, the rest is still okay. Right, so now this makes more sense, right? So if you look here, so Ka times Pa, when it's very small, that means that this term basically becomes 1, and you only are left with the top term, right? Oops, delete that. Up. And when it's very large, then you saturate and you go to 1. Okay, I don't know how I messed that up. Anyway, so the SIPs is still correct, right? Tot, Freundlich. So those are the different isotherms. So the difference with BET is that it's actually a model for multi-layer absorption, right? So it can explain also some physisorption, whereas SIPs, Tot, Freundlich, Langmuir, they all look at the binding sites, right? So there's only one binding site where it can bind. You cannot have molecules on top of molecules. Okay, so let's look at the reaction on a catalyst surface. Okay, so let's consider first we have a single species. So for example, A from the gas phase is in equilibrium with A adsorbed, and then A adsorbed reacts with Kr to B. And then for simplicity, people just say that, you know, once you react, that the desorption is basically so fast that you just don't regard it, right? So A adsorbs, goes straight to B in the gas phase. So the rate V would be Kr times theta A, which would be Kr times Ka times Pa over 1 plus Ka times Pa. Okay, so again, there can be these two regimes, right? So if we have weak absorption, or low pressure, then V weak would be Kr times Ka times Pa. So this is the same assumption, right? So if you have here, theta will be Ka times Pa. So if we just substitute that here, we get this regime. So this is a first order reaction. If we have strong absorption, or high pressure, V strong is Kr. So it becomes 0th order, which is nice. That's for single species. Let's see if we have 2 species, which is, I guess, more realistic, right? When you are looking at reactions. So we have A in the gas phase in equilibrium with A adsorbed. We have B in the gas phase in equilibrium with B adsorbed. And we have A adsorbed that reacts with B adsorbed. That goes to a product in the gas phase. So this one is called the Langmuir Hinchelwood model. Okay, and the rate for that is Kr times coverage of A times coverage of B. That becomes Kr times Ka times Pa times Kb times Pb, 1 plus Ka plus Kb squared. So this is again interesting, right? Because this says that the reaction rate should rise if we increase theta A or pressure of A and pressure of B, and then decline after a certain maximum. So how is that, right? Imagine that B, let's write 2 examples. So if we have both our strong adsorbers, then the rate will be roughly Pa times Pb. But if, let's say, B is a strong adsorber and A is weak, then we get Pa divided by Pb. So B is actually inhibiting. So you can imagine, let's say B is a strong adsorber. So it will occupy all the sites, right? Everything, all the sites S will be full of B. There's no A on the surface. So if there's no A on the surface, you cannot have a reaction, right? So you don't have products. So that's why for these kind of situations, I mean, typically both A and B are, relatively weak absorbers. So this problem doesn't arise much, but it could happen. And it has also been observed in some cases. But there's a maybe simpler model that doesn't have this same limitation. So if we have A from the gas phase in equilibrium with A adsorbed, and then we just say, okay, A adsorbed can directly react with B from the gas phase to give a product in the gas phase. So we kind of skip the fact that B maybe doesn't need to absorb. So we have Ely ideal conditions. And here the rate V is Kr times coverage of A times pressure of B, which would be Kr Ka times Pa times Bb over 1 plus Ka times Pa plus Kb times Pb. Right, and this equation, the reaction rate rises monotonically. Right, so it doesn't decrease if you would increase both coverage of A or the pressure of B. It can never go down, so you cannot have this kind of one of the species inhibiting the same surface. Okay, let's move to the last section, which is homogeneous catalysis. Okay, so everything in the same phase. Same phase. No, gas or liquid or supercritical or whatever you want. So let's look at an example. So 2 cerium 4 plus thallium Tl plus gives up to cerium 3 plus Tl3 plus. Okay, and this reaction is silver catalyzed. Okay, so let's look at the proposed mechanism. So we have silver plus, cerium 4 plus in an equilibrium with silver 2 plus C3 plus. Call this reaction 1. Silver 2 plus Tl plus. Silver plus Tl2 plus. And the last one, Tl2 plus cerium 4 plus gives Tl3 plus Ce3 plus. Okay, let's put some colors in this so it's easier to see. So we color cerium 3 plus gray. I'm gonna color this one. So those are the products. Color those yellow. I'm gonna do silver, green, and some blue here for silver 2 plus. Some orange here. Okay. Purple. There you go. It's easier to see. So let's look at the product, one of the products. So that's Tl3 plus dt, which is K3 times Tl2 plus Cerium 4 plus. Okay, so one observation we can make here is that TL2 plus, this one, is only formed. So let me just write it out. TL2 plus is an intermediate formed in reaction 2 and reaction 3 can only occur after 2. So we can make an assumption. So the velocity of reaction 2 would be roughly that of 3. So we can write TL3 plus dt is K2 times silver 2 plus times TL plus. Okay. So also if we look, silver 2 plus is also an intermediate, right? So it's the blue one here. Is another intermediate. So we can apply the steady state approximation. So there was a question this week from someone by email, like, when can I use the steady state approximation? And the real answer is, well, it's an assumption. So it's always more accurate to not make any assumptions. But let's say in the good old days, people wanted to write the, let's say, integrated form of your rate equations, right? And they are they quickly become unsolvable if you do not make any approximations. But so let's do this steady state approximation for now. But then actually it is more accurate to not make any approximations and do it numerically. So we'll do that as well. But let's first finish this up. So if we do steady state approximation, let's see if I can fit. Doesn't really fit. Okay, but I hope it fits on your paper. So we're going to write d Ag2 plus dt. So is K1 Ag plus Ce4 plus minus K minus 1. So the back reaction of the equilibrium, Ag2 plus Ce3 plus minus K2 Ag2 plus TL plus roughly 0. Okay, so from this we can write Ag2 plus is K1 Ag plus Ce4 plus K minus 1 times Ce3 plus K2 TL plus. Okay. So if we fill that out in the original rate we got from the previous step, then we get K1 times K2 Ag plus Ce4 plus TL plus over K minus 1 times C plus K2 TL plus. Right. So we have a nice rate equation for the products, or for one of the products at least. But I wanted to also, of course, implement this in an easier way, because this is still not an integrated form of the equation. So let's move 1 second to Spider. Okay, let me see where I have it. Where? Okay. Okay, so I implemented this system in Spider, as we've done together now a number of times. So I won't go and retype everything from scratch because it will take too long. But basically, I copied my equations that you have now on your paper. So, and I just simplified the notation a bit. So silver plus, I call it A1, and cerium 4 plus, I call it C4, silver 2 plus, cerium 3 plus, and so on and so on, right? So this is just to make your life a little bit easier. Here I put, as you see, a fast pre-equilibrium, right? So K1 and K minus 1 are a bit, quite a bit bigger than K2 and K3. So you have the pre-equilibrium, as is so loved with the steady state approximation. Then we start with our model, right? So I define all my species, and then I write for each of the species the rate equation. So if you look on your paper, for example, for silver 1, that is disappearing in reaction 1, right? So minus K1 times silver 1 times cerium 4, and it's also formed. It's the equilibrium, right? So K minus 1 times silver 2 times cerium 3, and it's also produced in the second reaction, right? So plus K2 times silver 2 times thallium 1, right? And so we can do all the rate equations for all the species, just as we've been doing all the time. We put them out. We define initial conditions. So we have initial, so this is the catalyst concentration, 0.1 molar. We don't have any of the intermediates, so silver 2 or cerium 3. These are the reactants. So we start with 2 molar of cerium 4, right? Because we use 2 of those. And then we have TL plus, where we start with 1 molar, and then also the products. Right, so the other intermediates, etc., are also 0. So we define a lin space, so from 0 to 50 seconds with 25 steps, and we call our integrator. So we run the model for the initial conditions for a given time, which will give all these concentrations out. So let me just reset everything 1 second. Set, yes, clear all. There we go. Okay, so let me comment this out for 1 second. So of course, the first thing we want to do is simply integrate. This is a kind of sanity check that I always like to do. So, well, let me just run it and then we'll see what happens. Okay. Oops, what is going on? Okay. So let's first look what was I saying? So check. So what I do when you get your first results out, so the integrated concentration, Cint, let's look at that one. Cint, I don't know if you can see this. Okay, there's a problem with my spider. But basically you have columns which have all the concentrations of all these species, right? So column 1 is A1 concentration versus time. Column 2 is A2 concentration versus time. And what I do here is I sum up all the rows. So if that value is constant, and it is, like if you look here in this check, it's always the same value, 3.1. Okay, 3.1, 3.1, 3.1, 3.1. Okay, so that's all fine. So that means the sum of all my species concentrations is constant, which means I'm not creating mass out of thin air or losing mass. So this is a common thing. If you have a mistake in your equations, you will either have, creation of new molecules or disappearance of molecules. So your mass balance over your entire system is not correct. So this is an easy check to make sure that your equations are good. So they're good. And then I'm going to make the first plot. So I'm just going to plot some of the different things. Let's see what that looks like. Okay, let me share the plot window. Here we go. Oh, did I share the wrong one? No, it should be good. Okay, so you see the initial concentrations, right? So I start with reactant CE4 plus at 2 molar. TL plus starts at 1 molar. They drop, they go to 0 eventually. And we see the product, so CE3 plus and TL3 plus are being formed in a 2-to-1 ratio. So that's actually correct. You can see, interestingly, the concentration of free catalyst, so silver, decreases initially a bit and then it recovers. So it does really act like a catalyst because overall it's not consumed, even though at the beginning it disappears for some time, but then it's recovered at the end. Okay, so that's nice. So what now if you are in your lab and you are you're measuring these kind of curves, right? So you measure the concentration of your maybe reactants or your products over time. Hopefully you have a technique which can give you enough data points as a function of time. So how do I now know, for example, the order in the catalyst, right? And so for that, there are all kind of different methods, but I want to highlight one, which is very simple. So that's why I'm just going to show it briefly. And it comes from this paper. Up, there we go. And so this is a paper by Jordi Bourès, and he compared different, or he's comparing different analysis, right? So far I've been telling you that, Langmuir plots are very nice, but what's the problem with Langmuir, right? You only use the initial velocity of your reaction. So I do a kinetic curve, I get some time trace. So here, one of the reactants is being consumed versus time. So Langmuir, you would fit only the initial velocity. And then you say, okay, that's the initial rate. And then you would plot the initial rate versus, for example, the catalyst concentration. And then maybe you do that on a log-log scale. And then you try to extract some information. But that means from all of this data, you only use like a couple points, like the first couple points, and the rest you throw it in a trash can. So given now that we have, nonlinear curve fitting tools available, we have Spider, it's really a shame that to not use this data. It's just that, in the times of Langmuir, Michaelis-Menten, there was no nonlinear regression tools as simple as Spider available, but now we have them. So let's use them. So this method is quite nice. It's very simplistic. Is because you basically replot all your curves where you multiply times the catalyst concentration to the power n. And the power n is then the order in the catalyst. And so in this paper, I put it on Moodle. They show some example catalytic cycle where they have some time traces, and then their method relies basically on your eyes. So when you multiply time times the concentration of catalyst to some power, and the power is actually the order of catalyst, and it's correct, then all these curves collapse onto one kind of master curve, and from that you can very easily determine the order of your catalyst. So I decided to do that also for our system. So for this simple example I just gave you for the silver catalysis, and so what we will do, okay, turn off. Did I show you this plot? Yes, I did. Okay, so I'll turn this plot off. And so what we need to do is, okay, we're not doing the actual experiment, of course, but I'm going to solve the model for a range of catalyst concentrations. Remember, so the catalyst is silver plus. So I define a range of concentrations from 0.01 molar to 5 molar, which is kind of high, but okay. And what I will do is I will make an empty array, which is filled with zeros. So this is numpy zeros. So it's like make an array which is full of zeros of the size, length of time, and length of my range of catalyst concentrations. So this is just pre-allocating memory. Okay. And then I will say, okay, for each of those numbers, okay, so I make an index 1, 2, 3, 4, 5, 6, 7. So this is, I is going to go from 0 to 6, because 7 numbers means 0 to 6 in Python. And I say, so of the length minus 1, I'm going to make this range, and then I'm going to say, okay, C0, so that was my initial concentrations, and the first one is my catalyst concentration. So I'm going to say, set the first value of C0 to this value in my cat range. So that's this line. So I say the first value of C0 will be cat range I, where I is 0, 1, 2, 3, 4, 5. Then I say, okay, use an integrator to find the concentration. So again, it's going to output an array which has 7 columns, right? C temp has 7 columns, 25 time points, because I put time 25 here. And so I calculate all the concentrations of all the species, and I say, define now this array, concentration catalyzed, where I only extract the third column, and the third column is C4, which is, you know, one of my reactants. Okay, so it's reactant concentration, and then okay, let's look what that, see what that looks like. I run this code. Okay, so let me share that window. So here you see concentration of one of my reactants versus time. And then you see that, so the blue curve is the lowest catalyst loading, and then we increase the amount of catalyst, the reaction goes faster and faster. So this is kind of what we expect. Go back to Spider. Okay, so what I did then is I actually moved all this code to Jupyter Notebook, which I'll quickly show, and then we can finish. Hub, there we go. Okay, so I'm in Google or in Jupyter Notebook right now. And so again, I'm just copy pasting the code. I'll put the scripts on Moodle as well. So I'm just, imported the code from Python. So I have, again, my rate constants. I have my model. I have my initial conditions, define my time. And then I copied this piece of solving the different catalyst concentrations. And I plot the time times the concentration of catalyst to some power p, right? And if this power p is correct, then we know the order of the catalyst. Okay, so let's run the script, and we see our concentration curves. Sorry, this is not time. This is, let me just correct that. So this is time times catalyst concentration to the power p. There we go. And we see that these curves are not overlapping. The power was set to 2. So this would be ordering catalyst 2. So now I can start dragging this around. And I see, okay, if I go below 1, it's pretty bad. If I increase, okay, this is of course a trivial example. So at 1, you see that all the data points for all the curves, so different catalyst concentrations, they all fall on top of each other. So this is a visual method to determine the order in your catalyst. In our example, of course, this was kind of trivial because this was, silver plus, which you can see from the equations that it's first order.
Hi, my name is Christian Nilsson, and in this video, I will show you how to apply visual kinetic analyses to obtain mechanistic information of chemical reactions. Some of these analyses use concentration against time profiles, which include the VTNA, or variable time normalization analysis, and others use reaction profiles of rate against concentration of reactant, referred to as RPKA, or reaction progress kinetic analysis. Concentration against time profiles are the most common in chemistry. They can be obtained by monitoring the reaction by NMR, IR, UV, or by simply sampling the reaction and analysing the aliquots by HPLC or GC. As such, we will first inspect the implementation of these analyses. To identify catalyst deactivation or product inhibition, we need to compare reactions started at a different point. In this example, the conditions of our standard reaction are the ones in red. So, to test for catalyst deactivation or product inhibition, we will set up another reaction with the estimated concentrations of reactants after the consumption of 0.5 molar of starting materials, for example. So in this case, 1.5 molar minus 0.5 molar is 1 molar, and likewise 1.3 molar minus 0.5 molar is 0.8 molar of B. This is shown in green. Then we will compare the reaction profiles of both reactions. In this case, we are going to monitor the concentration of B and compare the performance of both of these reactions from 0.8 molar onwards. At that point, both reactions have the same concentration of reactants, but the red reaction has 0.5 molar of product, and the catalyst has already completed 50 turnovers, so it could have suffered some deactivation. In order to compare both profiles, it is necessary to shift the curves horizontally. In this case, we can shift the green curve by 3.3 hours, so the two reaction profiles have approximately 0.8 molar at the same time. It is evident that in this case, both profiles are different, and the red reaction is slower. That can be due to the effect of the product generated in the red reaction until that time, 0.5 molar amount, or to the catalyst being deactivated. To discern between these two possibilities, a third experiment is run. The third experiment, here in blue, has the same concentrations as the green experiment, but also has the amount of product generated by the red experiment until that moment, 0.5 molar in this case. Thus, the horizontal shift of the reaction profile allows us to compare the performance of two reactions with identical concentrations of all the species, but where the catalyst has already been working for a while. In this case, both profiles now overlay perfectly, indicating that catalyst deactivation is insignificant, and the reason for the different performance of the red and green reactions was product inhibition. To elucidate the order in any component of a reaction, we have to compare profiles with different concentrations of that component and the same concentration of all other components. In this example, red will be our standard reaction, And in the three other reactions, we will change the initial concentration of A, as shown in green, concentration of B, as shown in blue, and the concentration of the catalyst, as shown in orange. To find the order in A, we're going to use the reaction with the different initial concentration of A, as shown in green, in this case using the profiles for appearance of product. We create the variable normalized timescale for the concentration of A using the formula for the VTNA, as shown in column D. The first value is 0. The second value has the VTNA formula, which is the previous value of the normalized timescale, D7, plus the concentration of A at that time, plus the concentration of A in the previous point, all divided by 2 and to the power of a constant cell, in this case B6, which is the order in A, and multiplied by the difference of time between both data points, C8 and C7. Then we only need to extend this down and use this timescale for the comparison plot. We do the same with the green experiment, and we plot both curves together. Now we only need to change the value of the cell B6 until we observe overlay. Clearly the curves have now crossed, and the green is above the red. Overlay was observed when the order in A was 1, and as such, this is the order of the reaction in A. We could also elucidate the order in A by monitoring the consumption of the reaction component B. The formula is identical to the one used in the previous sheet, so we modify the value of the cell B6 until we observe overlay in both curves. Again, we have found the order in A to be 1. We could also elucidate the order in A by monitoring its own consumption, but in order to compare both reaction profiles, it is necessary to shift vertically the reaction profiles until the starting point for both reactions is the same. This has been done in column F, which simply subtracts 0.4 molar from the real concentration of A. The normalization of the timescale has an identical formula to the one used in the two previous sheets, and again, by changing the value of the cell B6, we can determine the order of the reactant. Again, overlay is observed when the order in A is 1. To elucidate the order in B, we're going to use the standard reaction, as shown in red, and the blue reaction, which has the same concentrations for all of the components except for B. In this case, the formula to create the normalized timescale is the same as previously, but using the concentration of B instead of the concentration of A. This is the previous value of the normalized timescale, D7, plus the concentration of B at that time, plus the concentration of B in the previous point, all divided by 2 and powered to a constant cell, in this case B7, which represents the order in B, and this factor is multiplied by the difference of time between both data points, C8 and C7. Plotting the reaction profile using the normalized timescale for both reactions allows us to determine the order of the reactant. In this case, we're using the profile of appearance of product. To determine the order in B, we change the value of the cell B7 until overlay is observed. When the order in B is 1, the lines overlay. If we further increase this value, the lines have crossed. As such, the order in B is 1. Similarly, we can also determine the order in B using the disappearance of A. Again, this confirms that the order in B is 1. Finally, we can also determine the order in B by using the profiles of disappearance of B. But, as the two initial concentrations of B are not the same, we have to shift one of the two profiles vertically to facilitate the comparison. In this case, as the difference of initial concentrations of B is 0.2 molar, we have shifted the blue profile down by 0.2 molar, as shown in column I. Using the standard variable time normalization scale for both reaction profiles, we modify the value of cell B7, and again observe overlay when the order in B is 1. To determine the order in catalyst, we use two reactions with identical initial concentrations of reactant, but different initial concentrations of catalyst. We have used the standard variable normalization for the timescale, although, as the concentration of catalyst is constant during the entire course of the reaction, a constant variable normalization of the timescale would be enough. The formula used is the previous value of the normalized timescale, d7, plus the concentration of catalyst at that time, plus the concentration of catalyst in the previous point, all divided by 2 and powered to a constant cell, in this case B8, which represents the order in catalyst. And this factor is multiplied by the difference of time between both data points, C8 and C7. Plotting the product appearance against the normalized timescale for both reactions allows elucidation of the order in catalyst. Again, identification of overlay highlights the order in catalyst as 1. Similarly, we can use the profile for disappearance of A to confirm that the order in catalyst is 1. And finally, we can also monitor the consumption of B, again to confirm that the order in catalyst is 1. We can also use all of the profiles at the same time, and by removing the kinetic effect of all of the normalized substances, A, B, and catalyst, we can estimate the K-obs of the reaction. The formula for the variable normalization includes 3 terms, A, B, and catalyst, and is made of the previous value of the normalized timescale, d7, plus 1 term for the normalization of A that contains the concentration of A plus the concentration of A in the previous point divided by 2 and powered to the order in A, which is shown in the fixed cell B6. Then, the term for the normalization of B, which is concentration of B plus the previous concentration of B divided by 2 to the power of the fixed cell B7, which represents the order in B. And finally, the term for the normalization of the timescale by the concentration of catalyst, which is calculated by the concentration of catalyst plus the previous concentration divided by 2 to the power of the fixed cell B8, representing the order in catalyst. This is all multiplied by the difference in time between the current and previous data point. By using this total normalization with respect to the concentration of A, B, and the catalyst for the 4 reactions, we can estimate the K-obs. Setting up the correct order in A, the red and green profiles with different initial concentration of A overlay, but not the blue or the orange. Also choosing the correct order in B, as previously determined to be 1, the blue, red, and green profiles overlay. Also, all the profiles now become straight as a consequence of the fact that we have removed from the reaction profiles the kinetic effect of all of the kinetic driving forces changing during the course of the reaction, namely the concentrations of A and B. Finally, if we also set up the correct order in catalyst as previously determined to be 1, all profiles now overlay on a single straight line in which the slope of this line is approximately equal to the K-obs of the reaction, in this case 34.7 molar to the minus 2 per hour. The same treatment can be done using the profiles of disappearance of A, with the only precaution of shifting vertically the profiles so all start at the same point. In this case, we have shifted the profile of the green reaction up by 0.4 molar, as shown in column O. Again, by setting up the correct orders in A, B, and catalyst, all reaction profiles overlay in a single straight line where the slope is approximately equal to the negative K-obs of the reaction. Also, the concentration profiles of disappearance of B can be used by vertically shifting down the profile of the blue reaction, as shown in column U, so all the profiles start at the same point. Setting up the orders in A, B, and catalyst, as previously determined to be 1, causes all the profiles to overlay on a straight line, with the slope approximately being equal to the negative K-obs of the reaction. Now, we are going to see how to apply reaction progress kinetic analysis, or RPKA. The main difference between the previous analysis and this one is that RPKA requires high-quality rate data, usually acquired by calorimetry. As before, we will first see how to find out if there is significant catalyst deactivation or product inhibition. To do so, we will use reactions started at different points, referred to in the literature as same excess experiments, because the difference in concentration between the reactants is the same in both reactions. In this case, the green reaction emulates the conditions of the red reaction after the consumption of 0.5 molar of reactants, but without the product that the red reaction would have generated till that moment, and with fresh catalyst. The blue reaction is the same as the green one, but now includes the product generated in the red reaction after consumption of 0.5 molar of starting materials. As we're analysing the reaction by RpKa, now the plots are rate against concentration of one of the reactants, in this case B. If you're not familiar with these plots, notice that they should be read from the right to the left. As the reactant is consumed, the rate of reaction usually decreases. By comparing the red and green reactions, it is easy to see that both reactions have different rates for the same concentration of B, and implicitly also the same concentration of A. This fact suggests that there is product inhibition or significant catalyst deactivation. The comparison of the reaction profiles of the blue and red reactions, which have the same concentration of reactants and product from 0.8 molar of B to the end of the reaction, shows two overlaid curves. Therefore, we can conclude that the higher rate observed in the green reaction was indeed a consequence of product inhibition, and there is no significant catalyst deactivation. To find out the order of reaction in reactants and catalyst, we have chosen the same reactions that we have used for the VTNA in the previous Excel file. As explained before, the difference is that now we are going to use rate profiles instead of temporal concentration profiles. We can elucidate the order in A by using the red and green experiments. To do so, we need to create a new column for both reactions with rate divided by A to the power of order in A. The formula in column G is the rate at that moment, F8, divided by the concentration of A, D8, to the power of B6 as a fixed cell, which will be the order in A. We do the same for the green reaction in column L, and then these two columns are plotted against the concentration of B. Then, the value for the order in A is modified until both curves overlay. As such, the correct order in A is 1. The order in A can also be elucidated by using the red and blue reactions. Although these two experiments have the same initial concentration of A and different initial concentration of B, part of their reaction profiles can be compared to obtain the order in A. In particular, after the consumption of 0.2 molar of the reactants, the blue reaction will have the same concentration of B, 0.6 molar, and different concentration of A, 1 molar in the case of the red reaction, and 0.8 molar in the case of the blue reaction. Therefore, these sections of the reaction profiles can be used to elucidate the order in A, if we are sure that there is no product inhibition and no significant catalyst deactivation. Changing the value of the cell B6, it becomes clear that the profiles can be compared for concentrations of B that are smaller than 0.6 molar, and the order in A is 1. To find the order in B, it is necessary to compare reaction profiles from the moment when the concentration of A is the same, but the concentration of B is different. In the case of the red and blue reactions, the starting concentrations already satisfy this condition, so the entire reaction profiles can be used to elucidate the order in B. As we want to determine the order in B, the y-axis will now be rate divided by the concentration of B to the power of the order in B, in this case the fixed cell B7. Then this column is plotted against the concentration of A. By changing the value of the cell B7, we can find that the order in B is 1. As the total amount of A consumed in each reaction is different, only the section of reaction between 1 and 0.4 molar of A can be compared. Order in B may also be elucidated by using the red and green reactions. In this case, the sections of the reaction profiles valid for the comparison are between 0.6 molar and 0.4 molar of A, as both reactions can only be compared with the same concentration of A and different concentrations of B. As mentioned previously, this comparison between reaction profiles that does not correspond to the starting conditions of the reaction is only valid if there is no product inhibition or catalyst deactivation. Modifying the cell B7, again, it can be seen that the correct order of B is 1. This is a small section to discern overlay, and so obviously comparison of larger sections of reaction profiles is more adequate. So in this case, the use of the blue and red profiles, as previously discussed, would be recommended. To find the order in catalyst, we use the orange and red reactions, set up with different concentrations of catalyst. In this case, the rate must be normalized by the concentration of catalyst powered to the correct order in catalyst, as shown in cell B8. This normalized rate can now be analyzed against the concentration of B by changing the value of this cell. As shown, it is clear that the reaction is order 1 in catalyst. Similarly, we can elucidate the order in catalyst by plotting the normalized rate against the concentration of A. Again, this confirms that the reaction is order 1 in catalyst. Finally, the k-obs of the reaction can be estimated by normalizing the rate of the reaction by all of the components of the reaction minus one of the reactants, which is plotted in the x-axis. In this case, we are normalizing the rate of each reaction by the concentration of A and catalyst to their correct orders of reaction. And plotting it against the concentration of B to the correct order in B, as previously determined to be 1. If all of the orders of reactions are correct, and the effect of all of the components with a kinetic effect on the reaction rate are considered, all of the reaction profiles overlay on a straight line, which slope is approximately the k-obs of the reaction. This is the end of the video, where we first covered the visual kinetic analysis of profiles plotting concentration against time, and then profiles of rate against concentration of reactant. We hope this video has been useful to you. Of course, if you have any questions, please don't hesitate to contact us, and thank you very much for watching.